Hello everyone. In this video we are going to talk about resistors, and I know resistors are very commonplace and simple for mechatronics, but there might be some stuff in this video that you might not know about them. So if there are parts that you know, you can just fast forward, but I try to cover a bunch of topics about resistors. So resistors are passive elements, and by passive means that they don't need to be given energy from anywhere, right? They don't need to be plugged into a wall or battery or anything. They are reacting to the voltages and current passing through them, and they don't need a source of energy. Now, the first thing they do is dissipating energy. They convert electric energy into heat. We'll see the equation for that. But they have lots of applications. You might say, what is the application if your job is dissipating heat? Well, of course, one of it is to generate heat. You probably have seen all sorts of heaters that are working based on electricity, from stoves to, electric blankets to all sorts of heating elements, right? So that's one of that, but there is a lot more, like voltage divisions, like limiting currents, like signal conditioning, and so on. And they are very, very fundamental. So what kind of resistors do we have? They are in general fixed ones and variable ones. The fixed ones are the ones that their values don't change much, okay? Automatically. Their values depends on the temperature, but mostly, it's not significant. And we typically use them under some fixed or very, very small changes of temperature. So the resistance is going to stay the same. And we use them for all sorts of applications, as I said, limiting currents, voltage dividers, and so on and so forth. In electronics, if you have seen my videos, we use them for pull up and pull down resistors and so on. So there are all sorts of ones. The one that you see most around are these guys called carbon film resistors. These are kind of like the most common, cheapest ones that their stabilities are moderate, and they are used in consumer electronics and for low-cost applications. These are the cheaper ones, the ones that you buy a pack of them for just $1 or less or something like that. Now, if you want the resistance of them to be a little bit more accurate and their characteristics more stable and not changing so much, then you can use these, what we call metal film resistors. So you see them kind of similar to the other ones. Mostly the color is blue, and they are used for precision electronics and measurement circuits. Okay, so their appearance is the same. They all have these color bands, but again, you see that they are mostly made of metal films as opposed to carbon films, and they are more accurate. Their deviations from the nominal value is much less. Then, of course, if we want even higher precision, then we have these guys called wire wound resistors. So these are made of metal wires, very high precision, and they are used for where you need to go with high generation of heat or high power applications. Mostly their appearance is kind of green like that, but again, there are different colors based on the manufacturer. And then you have the ones that can act also as a fuse. We call them fusible resistors. So if too much current passes through them, they burn and they avoid excessive current to pass through the device they are connected to and burning that device. So they act as a fuse, and they are used in circuit protections and safety devices. And the appearance could look like this, white or any other color. Then we have the category of the ones that are variable. Either we manually change them or they change based on a parameter. So the ones that we change are like potentiometers, rheostats, and trimmers. Potentiometers, or you might call them pots or volumes, are the ones that you see in lots of different devices. So whenever you use a volume control or something, many of the dials that you have around you in your cars, everywhere, they are mostly a potentiometer, okay? And it's a variable resistor based on the location of this dial. The amount of the resistance that goes from one side of it to the other, the amount of the resistance that is between input output will change. Basically, that's a rotary voltage divider. And the portion of the resistance in the circuit, as I said, when it changes the balance of that voltage divider, so you can get different voltages or different resistances. Now, this is a rotary one. There is a linear one where the slider moves left and right. That's called a Resistor. And these guys are linear. Again, this is an entire resistance, and based on where this slider is, then the portion that takes the voltage out will be different. So you can have the entire length as the resistance, or a little bit of it, or half of it, or something. So it's a variable linear resistor. And then we have the ones that we call trimmers. And trimmers like these, typically when you want to change their values, you have to use a screwdriver. So you see their tips. They are basically designed such that you don't change them often. They are for precision applications where you just change these values and fine tune something and then leave it there. They are not meant for constant change of the variables, okay? They are for fine tuning. So you use these variable resistors for sensor calibrations, for dimmers, right? For volume controls and so on. And here I made a small table for you explaining the difference between a trimmer and a potentiometer or a Resistor. So a trimmer, as I said, typically is a small adjustable resistor, and it's for fine tuning, but potentiometer, you can continuously modify it. The size of trimmers are typically small. You can put them on PCBs, printed circuit boards. Potentiometers are typically a little bit larger, so you can grab them with hand. Adjustment of trimmers typically done with the screwdrivers, and it's infrequent adjustment. Potentiometers, you can do it by hand and frequently. Okay, so trimmers are for factory set calibrations or fine tuning. As I said, these are for general, basically changing up resistance. Trimmers are lower durability. They are not designed so you continuously change them. Potentiometers have higher durability. And as I said, potentiometers are used in volume controls, in audio devices, in dimmer circuits, in joystick controls. But trimmers are used for mostly sensor calibrations, fine tuning, and so on. Okay, so these blue guys that you see here, these are trimmers, and you typically use a screwdriver to tune them to exact value. So these are variable ones. The next group you have is called thermistors. Thermistors are the ones for which the resistance changes with temperature significantly. Now, either the temperature with resistance with temperature goes up or it goes down. If they go down, if their temperature goes down, resistance goes down with temperature, we call it NTC, negative temperature coefficient. If their resistance with temperature goes up, we call them PTC, positive temperature coefficient. And they typically look something like this, or they have an appearance like an LED where this portion here is black. Okay, so these are the ones that use for temperature sensors and make sure you don't have overcurrent protection or something. But mostly, as I said, they are used for temperature sensors. Okay, and finally we have the photoresistors. These are the resistors, or LDRs, light depending resistors. These are the ones for which the resistance depends on light. So if you shine light on them, the resistance will change. And they typically look like this. So you see kind of this resistance on this panel, and based on the light, how much light it is absorbing, the resistance of it is changing. These are typically used for automatic lighting systems and camera exposures. Okay, so these are the common type of resistors that they are available in the market. Now, about the thermistors, as I said, the temperature affects the resistance. How? Is that a linear effect or is it a nonlinear? And the matter of fact is the thermistors, they are nonlinear elements. So if you look at, for instance, an NTC, you see that the resistance drops with temperature in a nonlinear fashion. The question is, what kind of function is that? That function is what we call Steinhard-Hart equation. And this is a function of T versus R as opposed to R versus T. So you see the reciprocal of T is a function of a polynomial of natural logs of resistance. So if you want to find R as a function of T, it's not possible. Okay? Because first of all, this is a cubic one, and you cannot directly solve it as a function of n, and then that's natural of R, not R, so you have to take exponential. So in general, it's an exponential relation, as you can see. Now you can approximate this relation. Instead of finding R from T here directly, which is almost impossible, you can approximate this equation, right? And say R is this exponential behavior. R naught times exponential of beta 1 over T minus 1 over T naught, where T naught and R naught are your set temperature and resistance, one single point on this curve. Beta is what we call the material dependent constant, and T is the temperature in Kelvin. It's absolute temperature. The same goes for this formula. This T here is the absolute temperature. It's not in Celsius or Fahrenheit. This is in kelvins. And in this equation, in the original equation, these A, B, and C's are what we call Steinhard-Hart coefficients. And the way you determine them is experimentally. Okay, so thermistors are nonlinear elements. They are not linear, and when you look at their data sheets, they should give you ABC, or they should give you R naught, T naught, and beta in order to determine at any temperature what is their resistance. Okay? Now, for resistors, there are some formulas that you probably mostly have seen. The most important one is the Ohm's law that says the voltage across a resistor is equal to the current that is passing through it times its resistance. Okay, that's the most important one, the most frequent equation that you use in electric circuits. Use it all the time, and that is very important. Now, of course, this resistance itself of the material, it depends on some properties. What properties? The resistance of a resistor depends on three parameters, rho, L, and A. A is the cross section of the resistor, L is the length of the resistor, and rho, which depends on material, is what we call resistivity. So, for instance, the resistivity of copper or aluminum is what different from a material that is not conductive. Material that are not conductive, they have very large rhos. Material that are good conductors, like copper or aluminum, they have smaller rhos. Okay, and L is again the length, and A is the cross section. So longer resistors, they have bigger resistance. Thicker ones, they have a smaller resistance because the cross section is bigger. So this is the resistance formula based on the physical property and the material. Good. Now, what else do we have? The next one is power dissipation. Remember, we said it converts power to heat. What is the equation for the power of that heat generated? The power in an electric resistor is voltage times the current. Now, since voltage is IR, if you replace it, you're going to get I squared R. Or if you replace I here, you say I is V over R. And you replace it here, it's going to be V times V over R. It's going to be V squared over R. So any of these three formulas, if you use, that is the power of a resistor that is converted into heat. Okay? So if you turn on a resistor with, let's say, a resistance of 1 kilo, and the current passing through it, or connected to a voltage of, let's say, 12 volts, and let this guy be on for a time of, let's say, 1 hour. How much energy has it used? You can say that W is P times delta T, because in this case P is constant, and since I have V and R, it's going to be V squared over R times delta T. Okay, so if you calculate this, you see that the wattage of it is 0.144, or about 15 hundredths of a watt. And the energy that it used during this time is 518 joules. Okay, or some people use kilowatt hour, which is a much bigger unit of this. Okay, so when you say light is 60 watts, you know what it means, right? Say the light is 60 watts and then the voltage of it is basically, let's say 120 volts. So you know by comparing these, 60 equals 120 squared divided by what, correct? Or if it's just volt times ampere, that is volt times ampere. You see the amp is 1/2 amp. Or you can find the resistance of it as well here. Okay, which you can simplify and get the resistance. So this is this power formula for a resistance. That is a very, very important formula. And the next two that are very important are when you put them in series or in parallel and you want to find the equivalent. So if they are in series, the equivalent of all of these ones that are in series is simply summation of them, which is clearly bigger than all individual ones. And if you put them in parallel, of course, 1 over reciprocal is going to be summation of 1 over reciprocal of all other ones. And in this case, the equivalent one is going to be smaller than all of these individual ones. So basically, when we put resistors in series, the goal is to make the resistance go up. We want to get a bigger resistance. When we put them in parallel, the goal is to put the total equivalent resistance down. We want to make the resistance smaller. Okay? So, and it's not really hard to show that in this case when you have them in series. So if you call them R1, 2, 3, there is one single current that is going through all of them, because at each junction here, all the current going in is the same as current going out. And if you call them I2 and I3, you see they are the same, I1 and R2 the same. So all the I's of these elements are the same. So I1 equals I2 equals I3 equals the total I. But the voltage drop across each one of them, V1, V2, V3, when you add them all, that's equal to total voltage. That's the Kirchhoff voltage law, right? So V equals V1 plus V2 plus V3. Now V is, in this circuit, is equal to the I times R equivalent. V1, based on the Ohm's law that we just learned, is R1 I1. V2 is I2 R2. And V3 is I3 R3. But remember, all the I's are equal. We just said that, so we can get rid of them. And you see R equivalent is summation of the other I's. So it's not really hard to show that. And in the case that they are parallel, also, again, it's not really hard to show that as well. Why? Because in this case, let's say I have two of them, or as many as you want. In this case, the current that comes into this joint, this node, will be split into I1 and I2. It goes in, right? So sum of those two I's is equal to the total I. And then the voltages are the same. So the voltage between this point and this point is the total voltage. That's also equal to V1. That's also equal to V2. So you can see that V equals V1 equals V2. Now I's, you know, I's are V over R. So this is V1 over R1. This is V2 over R2. And that is V over R equivalent. Since the V's are equal, now we can get rid of these V's. And we get 1 over R equivalent is 1 over R1 plus 1 over R2, which is exactly this formula. If there are two of them, if there are only two, you can show that R equivalent is going to be R1 times R2 divided by R1 plus R2. If you simplify this relation, this is going to be the equivalent. Okay, and you can clearly see it's less than both R1 and R2 because this coefficient here, this is less than 1. Or if you look at it for R1, this coefficient is also less than 1. So this is less than both R1 and R2 in here, okay? Very fast, one other thing that I need to tell you about this is, so if you look at this series case, we learned that the voltages 1, 2, 3, they are not all the same, right? They are different. But how is each one of them calculated? So V1, remember, is R1 times I, and I was V over R equivalent, and R equivalent is R1 plus R2, so it is going to be R1 over R1 plus R2 times V. And similarly, you can show that V2, which is R2I, and I is the same I, it is going to be R2 over R1 plus R2 times V. So what are you doing? You are saying that if you look at the ratio between V1 and V2, that's the same ratio between R1 and R2, because the rest of it is constant. This term here, that's the same in both of them. So you are saying that the resistor that is bigger, it's going to get a bigger voltage. So if I only have two of them, let's get rid of this for a moment. If this guy is R and this guy is 2R, how much are the voltages? If this whole voltage is V, this guy should take 2 times more than the other one, because the voltage of it is, the resistance of it is 2 times bigger. So this guy is going to get 1/3 of the voltage. This guy is going to get 2/3 of the voltage. And this thing that you see here, that I divided the total voltage between them, this is called the voltage divider. So when we say we use resistances to divide the voltage, this is what it is. Basically putting two resistors in series and dividing the total voltage among them based on the ratio of their resistances. Okay, that is called a voltage divider. And when you have a rheostat, so what you have in a rheostat is you have these two resistors side by side, but this junction point is determined by the location of the slider, because the whole thing is like resistor, resistor, resistor. So when you put it here, one of your resistors will be this, the other one will be this. Which one is bigger? The one that is longer, because we just learned that resistance depends on the length. So if you put it 1/3 in between, this guy is like 2R, this guy is like R, or this is like R over 3, this is like 2R over 3. So this portion takes 1/3 of the voltage, this portion takes 2/3 of the voltage. Do you see that? But if I bring it here in the middle, now they're both going to be R over 2 and R over 2. Yes? In this case, both voltages will also be V over 2 and V over 2. And if I move it further, now this side is going to be bigger than the right side. This voltage is going to be bigger. So by moving the location of that slider, I'm splitting the resistance, the big resistance, between two smaller ones in series, and I'm doing the voltage division. So that is the voltage divider. And in series, just let me show you, remember the I's are not the same, but which one I is bigger? Remember, I1 is what? I1 is V, or V1, because V is the same as V1 over R1. V1 is the same as V, so we're going to write it like that. And I2, if I write it, that's V2 over R2. And V2 is also the same as V, so it's going to be V over R2. And from these two, if you see that their numerators are the same, but denominators are not. So you can see that I1 over R2 is R2 over R1. In other words, the circuit, the branch that has smaller resistance is going to take the bigger current, right? between these two branches, which one of them will attract more current to it? The one that has a smaller resistance. That's why when there is no resistance and you only have a wire instead of a resistance, what's going to happen? When one of them has a significant resistance and the other one doesn't, this goes to zero. What happens to I1? I1 goes to infinity, in theory. What does that mean? It means all of your current is going to come through this branch that has no resistance and nothing goes through there. What do we call that? Yes, that's the short circuit. So short circuit is when one branch has no resistance, so all the current passes through that. The other branch gets nothing. That's the short circuit. So you see, the short circuit and the voltage dividers can easily be explained by series and parallel what? Resistors. We also looked at thermistors. We also looked at difference between potentiometer and trimmers and different types of resistors. The last part that I want to explain, and a little bit of that I did in my previous videos, is how to read a resistor just by looking at it. Of course, you can always connect them to a multimeter and read them, but it's good to know how to read them based on these color bands. Okay, so if it's a 4-band resistor, so you see 4 color bands, the way you read it is this. The first band is going to be the first digit, the second band is the second digit, the third band is the power of 10 multiplier, and the fourth band is a tolerance. So, what does it mean? The first band is a brown. You go and see brown means 1. So the first number is 1. The next one is black. Black means 0. Right? So 1, 0. The next one is an orange here. What does orange mean? Orange means 3. So this is a 3. And then yellow, gold, sorry. Gold means plus minus 5%. So what is this resistance? It's 10 times 10 to the 3. It's 10 times 10 to the what? To the 3, which is 10K. So that's a 10K resistor plus minus 5%. What is 5% of 10K? That's right, that's 50. So it is going to be 10K plus minus 50. So the maximum of this should be 10,050 ohms. The minimum of it should be 9,950 ohms. So this is what? This is your resistance. Gold means it has a smaller tolerance. Silver, if the last band is silver, that means it has a bigger tolerance, plus minus 10%. So brown, black, and orange means a 10K resistor. With gold means 5% tolerance. Okay, this is very simple. Now, sometimes you might have 5 or 6 band resistors. This I did not mention in my previous video. So the one that I just showed you was 4 band. The 3 band does not have a tolerance band. But what is 4 and 5? 5 and 6, I'm sorry. Well, that's all it is. If it's 5 and 6, then the first band is the first number, second and third band are second and third number. The fourth one is the multiplier, which is that 10 to the whatever power. The fifth one is a tolerance, again, gold and silver. And there is a 6th band. The 6th band is a temperature coefficient. Okay? So how do you read that? Let's take a look. So again, the table is very similar for black to white. It's the same numbers, 0, 1 to 9. Gold and silver still mean 5% and 10% tolerance. Okay? For multiplier, there is also a pink. And then we talk about the temperature coefficient. So first, let's read one of these and then discuss it. So let's look at this last one. What is this last one doing? How much is it? What does it mean? If I look at this last one. So first band is brown. Brown means 1. So this is 1. Second band is black. That means 0. Third band here is red. Red is 2. Multiplier is blue. Blue is 6. Tolerance is gold, means 5%. And temperature coefficient, that is basically a green, right? And if you look here, right, there is only one green, that is 5, and plus minus 20. So this is plus minus 20. What is the unit? ppm per Celsius. So what does it mean? So what is the number? First of all, the number is 102, so 102 times 10 to the 6. So it's 102 mega ohm plus minus 5% of it. So you have to calculate 5% of that, right? So that is going to be 510, right? So it's going to be plus minus 5.1 mega ohm. That's your tolerance. That is under room temperature. So you are at 102 plus minus 5, so you can go to 97 and 107. Okay, that's your resistance, mega ohm. And then 20 part per million. What does it mean? Means this number, let's say it's just 102. This number, if the temperature changes, 20 part per million, so 20 divided by 1 million, times the change in degrees Celsius is how much it can change from the original value. So let's say, for instance, the temperature goes from the room temperature to room temperature plus 50 Celsius. So you heat the environment by 50 Celsius. So this is 50. So 50 times 20 is 1,000 divided by 1 million. That's just going to be 0.001. Of what? Of the original value. So 0.01 of 102 mega ohm is going to be 102 kilo. So the number is going to be 102 mega ohm, and then plus and minus what? 102 kilo ohm, because the temperature changed by what? By 50 degrees Celsius. So ppm is part per million. And this is how you read the temperature coefficient. Now you see, this is not major. This is a very small number compared to that. Okay? These are very small numbers. So the resistance here does not change big time with temperature. So these are not good for measuring temperature changes because their changes are very small. You need something for which the resistance changes significantly with temperature, like a thermistor, and it behaves non-linearly. Okay, so these ones you cannot use for thermistor applications. And finally, as I mentioned, there are different applications for resistors. There is voltage division that I said. There is heat generation that I said. They limit the current that goes to all sorts of devices, from transistors, from LEDs, and all sorts of other things. I have a video on the channel under mechatronics playlist, and you see I calculated for you how much of resistance you need for LED. And if you remember, I showed you that it was 220 ohms. Let's see if I still have it. I guess it was this one. Yeah. So I calculated for you that you need 220, and the explanation was that the voltage here you are putting behind it is 5 volts, right? You see? And then the voltage you need behind the LED is 2.2, and the current that the LED can tolerate is about 15 milliamps before it burns. So you need 220 ohms to make sure the LED doesn't burn. And you'll see later when I do my transistors, we also need to calculate appropriate resistors and put them next to the collector or next to the base of the transistor and make sure the current does not surpass the limits of the transistor. And of course, we use them in amplifiers. If you look at op amps, Op amps, they have transistors and resistors for amplification, and actually the amplification factor is the ratio of two resistors. If you watched my op amp video, we use them in filters like RC filter. The time constant for RC filter is R times C. So if I change R, I change the time constant, or I can change the cutoff frequency of the low pass filter of that. And there are timing circuits and so on as well. Okay, so there are lots and lots of applications of resistors, and as I go through my videos, you're going to see more and more of their applications because resistors are everywhere. So hopefully I could give you enough of information for resistors in this video, and I'll see you in the next lecture. Thank you.